Hello and welcome to my Physics 2211 Physics Lab 4, the Oscillation Lab. For this lab, we will use Newton's second law to predict motion and the energy principle to do much of our analysis. The forces in this example are the spring force and gravitation force. To do this lab, I used a tracker to track the mass as it moves. I set the origin to be the fixed point at the end and set the initial distance of the string to be 0.7 meters. This allows us to have a scaled representation and allows us to take accurate data. I then tracked the mass over time and I exported the X and Y data to Excel. This will be used to analyze the difference between the model and the tracked data. The mass of the object was 0.402 kilograms and we will try to get K, the spring constant, and L naught. To do this, we will use the formula that the time or period of oscillation is equal to 2 pi the square root of mass over the K constant. Using algebra, we isolate the K constant and get that the spring constant is equal to 4 pi squared times mass over the period t. So now let's find t. To do this, we will see how long it took the mass to return to its initial position. So I will be looking at the fifth time the spring made a complete oscillation, and this was at time 9.117 seconds. And then we divide by the amount of times that it oscillated between this, and we get that the time or period is 1.5195. This allowed us to calculate the spring constant, which we found to be 10.44. Knowing that at equilibrium, force of the spring and force of gravity are equal, we will find that the relaxed length of the spring is equal to 0.2607 meters. To do this, we set Fg and Fs equal to each other and plugged in all the values we know and solved for L naught. We can now start coding in the Python code. For the code, I first had to edit the initial conditions of the system. This included mostly recording or data recorded from the tracker. I then had to initialize the position and velocity vectors to start. This data was used to get the data for the spring force and then the net force when combined with gravity. This allowed us to get F net, which would then be used to update the position and velocity of the ball over time. We then went into the energy part where we defined each of the energies that the system has, shown on screen now. Because there is no energy coming from the outside of the system, there should be no net force in the end. They should all cancel out. After doing this, we set the model to run. The model does work well when compared to the data. The data did have some variability and a loss of energy due to either mass tracking or friction. However, the model is a very close representation to what actually happened. So, to answer the questions, what does this mean? The energy principle is satisfied by the model because there is zero net energy. This is because the energy is transferred from one form to another instead of being lost or gained in some other way, therefore adhering to the law that no energy is created or lost, only transferred from one form to another. And then for the period of oscillation in the x direction versus the y direction, the period in the relation to the y movement is shorter. This is because the spring and gravity forces are slowly equaling out and decreasing the period. There's also more force in the y direction, which causes the mass to change directions a little bit faster when compared to the x, which only has the spring force in the x direction to affect the motion and change directions. This is why the period in the x direction is greater, or a longer time.